On a kind of high level here, what we're doing is we're taking an RGB input from a camera, and we're going to use an expensive operation like a neural network to extract the depths from that camera. And then we're going to see if we can make this more efficient by, for future time steps, using a more effective algorithm that doesn't need to use such a computationally heavy algorithm as a neural network. And the real question we want to decide here is, when can we switch between these two operations? Between our expensive neural network and our efficient algorithm, which we present called MADP. So here's some basic context and assumptions that we'll be following throughout the presentation. Again, we're considering vehicle autonomy, and this can either be a car or it can be a drone. The most important thing is that we consider the vehicle to be equipped with a forward-facing RGB camera. So this monocular camera where you cannot get the depths directly from the camera. So we're going to evaluate on two beds. The first one is a real-world kitty data set, and this is used primarily for car navigation. And the second one is on the robust drone similar Microsoft AirSim. Now the advantage for the simulator is, of course, we can launch to any point in time and space whenever we want and collect an observation. We can render physics and any collisions along the way. Whereas with a real-world data set, we are fixed to the path that the data was collected on, and we have no freedom to move around in space and time. However, the simulator isn't as realistic, thus that's why the kitty is called a real world, so we use both testbed environments for comparisons. So the main task is to take in an RGB camera input, extract the depth, and then we're going to use our efficient algorithm to then further extrapolate the depths to future frames while it's saving resources. And we're going to use those depth maps to help avoid any collisions while navigating between 2 points. So here's our entire system model laid out a little bit more. We'll go through each of these panels. So now what we want to do is that we have our operations. We want to optimize the total amount of resources spent while executing these computations, and that's in form of time, power, and energy while it's navigating from point A to point B. So there's three core operations here that we're going to be cycling through. Operation A is using a neural network to extract a 2D depth map from an RGB image. Operation B is to use our more efficient algorithm called MADP, which will extract those depths from the image. However, it's saving on computational resources and it will be less accurate. And then Operation C, which will then use this depth map, whether it's from Operation A or B, to then input into a navigation module that would decide how to safely navigate between 2 points. So SmartDepth, which we've called this, is it's kind of intelligently deciding which of these depth maps to use, is the algorithm that determines how we create the depth map, either Operation A from the neural network or Operation B, our MADP algorithm, which I go over in the next slide. And then it will use those to navigate between 2 points. So here's our MADP algorithm that we use. So the way this works is it starts from a high fidelity reference frame, which in this case is the 2D depth map from the neural network. What it'll do is it'll calculate motion detected from objects in the camera scene. So this is, bicycles, cars, pedestrians, etc. And then it will cast the 2D depth space from the depth extraction from the neural network into a 3D point cloud. So it knows where all the X, Y, Z position of all the objects and where they are. And then what we're going to do is we're going to propagate that forward. We're going to pretend that the drone or vehicle is making a step forward in time. It's going to move through this 3D space. And then what we're going to do is capture an observation at some proposed time frame. Say it's moving forward 2 meters or 4 meters or 10 meters. And then we're going to reproject that 3D space back to a 2D map. And now we have our nice 2D map at any point in time and space that we want. So here's some results that show how this works. So you can see in the top how when we execute further ahead in time using this MADP algorithm that the predictions spread out and they become worse. This is expected because as you go further in time, you have less data to work with, so it's not going to be as good. And this is really the optimization algorithm that we're trying to solve here, right? How forward in time can we predict before this MADP algorithm is no longer useful? And what we show here in the bottom left is exactly that. So we show as we predict further in time, taking bigger steps, that accuracy nominally drops while we get these significant reductions in computational resources. Thank you.